Hello students. Now in this video let's start chapter 2, that is transportation problem, or in short it is known as TP. The TP is one of the subclasses of LPP in which objective is to transport various quantities of a single homogeneous community that are initially stored at various origins to different destinations in such a way that the total transportation cost is minimum. We can represent the TP or the transportation problem in the following tabular form. Called as the transportation table. So how was the tabular form? Let's see that. The tabular form is as here. The tabular form is as such. Here in this side the destinations, towards this side. Suppose first destination D1, second one D2, and so on up to Dn. Suppose we have Dn destinations, and here origin to this side. Suppose first origin, second origin, and so on up to mth origin. Here demand is suppose B1, B2, and so on up to what? Bn. And here supply supply. Suppose A1, A2 and so on up to what? AM. And here this demand and supply, this total is here. Okay. Now what does these here we have the cost, that is C11. Here the cost C12 and so on up to here the cost C1n. Similarly here the cost C21, C22 and so on up to C2n. Again here this CM1, this is CM2 and so on up to this is CMN. Here the variable is X11, X12 and X1n. Here X21, X22 and X2n. Here this one also. Okay. Here XM1, XM2 and XMN. As such the variables we can write. So here, or we can say where, what is cells? The MN cells, the MN large squares are called the cells. Large squares means these one, having the cost. This is the cell, this is also a cell and so on up to these are cells. So these are our cells. These are MN squares, MN large squares having cost and the variable also. Now another thing here, the variable Xij represents Xij. This is X11, X12 and so on up to Xij represents the quantity to be transport from origin OI to destination DJ, and OI to destination DJ, and Cij is the cost of transportation per unit. Cost of transportation per unit means this C11 is a cost of transportation from O1 to D1. C12 is a cost of transportation per unit. For a single unit, it is a cost of transportation from O1 to D2. Again, C1n is the cost of transportation for a single unit from O1 to Dn. Similarly, CMN is a cost of transportation from OM to Dn. OM is the origin. From here we can transport this to this destination Dn. This is the meaning of this. Now let me give one example for this. Example for TP. The example is given as such. A tabular form is given to us. Suppose example with us. Destination and here origin. D1, D2, D3 and D4. Supply and origin O1, O2, O3 and demand. Here the costs are given. Here the cost is 1 means rupees 1. Here the cost is rupees 2 is given to us. Here again rupees 1 and here 4. Here 3, 2 and 1. Here 4, 2, 5 and 9. And demands are 20, 40, 30 and 10. These are the demands from these destinations. And the supply from the origin, possibilities of supply. Here 30, 50 and 20. Look at this total and this total, both are how much? 100. Here we can write the total. As such, the problem of transportation is given to us. So now further let's see how to write it in the form of linear programming problem or in LPP. Same example I am taking here, and suppose we have to write this in a linear programming problem. So let me write here, this is transportation problem of the LPP. Let's write the LPP now. What was the objective function? Now we know anyhow, and also in definition we have seen that the transportation cost we have to minimize from while transporting the whatever quantities from one origin to the another destination. So here the objective function should be of minimization type. So what can we write? Minimize z equal to, what is here? Here the variable is what? x11. So x11, x12, x13 and x14 is here. x21, x22, x23 and x24. x31, x32, x33 and x34. These one. So minimize z. What was z? This product we have to take. So here we get x11 plus 2 times x12 plus x13 plus 4x14 plus 3x21 plus 3x22 plus 2x23 plus x24 plus 4x31 plus 2x32 plus 5x33 plus 9x34. This is our objective function. Here we have to take a product of Cij with Xij, and we have to add them. Summation of I from 1 to 3, j from 1 to 4, and Xij into Cij. That thing we have to do here. Now constants. So let me write subject to. Subject to. Now here two types of constants. First one, the supply constraint, and another one are the demand constraint. So supply constraint are row wise. So this x11, x12, x13, x14, their addition should be how much? 30. Similarly the other, and demand constraint are these column wise. So this x11 plus x21 plus x31 should be how much? 20. Similarly the others. So let me write first supply constraint. Supply constraints. Supply constraints are what? x11 plus x12 plus x13 plus x14, and here equality constraints are these, equal to how much? 30. Again x21 plus x22 plus x23 plus x24 is equal to what? 50. Again x31 plus x32 plus x33 plus x34 is equal to what? 20. Now demand constraints. Let's write the demand constraints. Demand constraints. So what does they? x11 plus x21 plus x31 equal to 20. x12 plus x22 plus x32 is equal to 40. Again x13 plus x23 plus x33 equal to 30. And last one, x14 plus x24 plus x34 is equal to what? 10. Such that these one, such that what? All these xij's should be what? Positive. Non-negativity constraints, such that xij greater equal what? 0. For I goes from 1 to 3 as a rows, and j from 1 2 3 4. This is a required representation of transportation problem into the linear programming problem. Now let me write the general form of this. So in general the m by n TP can be formulated the general LPP as minimize z equal to summation I go from 1 to m, j goes from 1 to n, xij into cij, subject to summation xij j from 1 to n equal to aij I from 1 to m. Again, summation xij, here I from 1 to m equal to bij, j from 1 to n. Okay, such that what all xij are what greater equal 0 for all ij. I can write it as such. So this is a general form of transportation problem into LPP. Now let's see some important definitions. Some definitions. So first definition is of allocations. In order to get the solution to the given transportation problem, we have to allocate the quantity xij to some cells from mn number of cells. The allocated variable xij generally shown by the circle in respective cell. Circle in respective cell. For example, xij, and we have to circle it. Now here the allocated cell is known as occupied cell or stone square. And an empty cell that is unoccupied cells are known as water square. Are known as water square. Now another definition. Here, what is this allocation exactly? We will see the example that time. It will be very clear to you. Now second definition is of feasible solution. Now these definitions are familiar to you from the first chapter, that linear programming problem. A set of non-negative values xij which satisfies the constraints in the transportation problem is called as the feasible solution. The values of xij means the variable which satisfies the constraints of the transportation problem is called what? The feasible solution. The same thing is in LPP also. Fine. Now the third definition is of basic feasible solution. Basic feasible solution. Or we can say BFS, basic feasible solution, or BFS. A feasible solution is said to be basic feasible solution is said to be basic feasible solution if the total number of positive allocations, if the total number of positive allocations xij is exactly equal to m plus n minus 1. Now, while finding these allocations, we will check whether that is equal to number of columns plus number of rows minus 1 or not. Okay, if it is, then we are naming it as a basic feasible solution. Now the next definition, optimal solution. The feasible solution not necessarily basic is said to be optimal if it minimizes the total transportation cost. Now the next definition is of balanced TP. So fifth definition, that is of balanced TP and existence of optimal solution. Existence of optimal solution. Now, if total supply is equal to total demand in TP is said to be balanced. Otherwise unbalanced. In short, if summation AI equal to summation Bj implies TP is balanced. And if summation AI is not equal to summation Bj implies TP is unbalanced. As summation AI equal to summation Bj or implies feasible solution Xij exist because Xij greater equal 0 and Xij is less equal minimum of AI and Bj. Okay, and that gives us there always exist an optimal solution to a TP. There always exists an optimal solution to a TP. Now, here we will stop. In next video, we will see how to determine initial basic feasible solution. There are 3 different methods to determine initial basic feasible solution in transportation problem. We will see them one by one in next video. Thank you.